Okay, so like I said, today we will be taking derivatives with respect to time instead of with respect to x. So at the beginning of our notes here, it says that we're going to be using implicit differentiation. That just means that the function may or may not be solved for y. And then we're going to use that to solve related rates problems. Related rates means comparing one variable to another one. The change in one, or the rate of change of one variable compared to the rate of change of another. So for the first problem, here's our function, y equals 4 radical x. You should have some idea of what that function looks like. Radical x is just this, and if it's 4 times that, it's just going to be higher by a factor of 4. So that's the way the function looks. It says to find dy dt when x equals 9, given that dx dt is 8. So this is saying that when x is 9, right about here, they're telling us that the change in the x has a rate of change of 8 units per minute or second, whatever we're using. So that's how fast that's moving. And they want us to find the change in y with respect to time. So how fast is the y value changing? So that's what we're going to be looking at. So the way that we do this is, we look at our problem, we're going to take the derivative of y. Well, the derivative of y is going to be 1 dy dt. To take the derivative of this side, I want to think of this as y equals 4x to the 1/2. It's a lot easier to take the derivative that way. So Avery, what's the derivative of 4x to the 1/2? Good. Now, we're not used to putting anything after the x, because normally we take the derivative with respect to x. But because we're taking the derivative with respect to t, I have to put dx dt after it. If we were taking the derivative with respect to x, I wouldn't need to put anything after it because it would be dx dx. But we're taking the derivative with respect to time, so it's dx dt. So now I'm just going to rewrite this. dy dt equals, if I have x to the negative 1/2, where is that going to go? Make it a positive exponent. Goes to the bottom, so it's going to be 2 over radical x dx dt. And now it's just a matter of substituting in. So we're going to plug in 9 for x, so then dy dt is going to equal 2 over radical 9 for the bottom, the denominator. dx dt is 8, so I'm going to plug in 8 there. So I'm going to have 2/3 times 8, which is 16/3. So for this specific point in time, when x is 9, when dx dt is changing at a rate of 8, here's the speed that dy dt would be changing. For part B, same problem. It's just that now they want us to solve for dx dt when x is 16. So way out here, when x is 16, given that the y value is changing at a rate of 9, how fast is the x changing? Well, now we're going to still use that same derivative. There's no sense finding it again when we already have it. And now we're just going to substitute in our values into the appropriate places. So dy dt is given as 9, plug it in. X is 16, substitute that in. And dx dt is what we're going to solve for. Well, the square root of 16 is 4. So we're going to have 9 equals 2 over 4 is 1/2 dx dt. So what's dx dt going to be then? 18, right? We'd multiply by 2. Dividing by 1/2 is multiplying by 2. So dx dt would be 18. So at this specific time, at these values, you can see that the x is increasing at twice the rate of y. Over here, x was still increasing, but is not at twice the rate like it was over here. So that's something that we have to keep in mind, is that these are not always going to be constant. It's not true that at every point it's going to be the same proportionality. Okay. All right, let's look at number 2 now. A point is moving along the graph of the function such that dx dt, meaning the change in x with respect to time, is 3 centimeters per second. Find dy dt for the specified values of x. Here's our function. You may or may not know what that looks like. It's not necessary really to know what it looks like. But these are values we're given, as well as this information right here. So what are we going to do first with this? Take the derivative with respect to not x, but time, with respect to time. So I might want to rewrite this. The way it is now, I'm going to have to use the quotient rule here. But I can rewrite this as 2 times 1 minus x squared to what power? -1. That's going to make the problem easier to do because now I can just use the chain rule on it instead of the quotient rule. But if you're good with the quotient rule, you could have kept it. If this -1, if that wasn't there, then I could distribute the 2 and make it even easier. But if it's to another power, I'm not allowed to distribute. I'm just going to have to go ahead and do it as is. So what's the derivative of y with respect to t? dy dt is right. To do this derivative, this is ku to the n. The derivative of ku to the n is k times n. So this derivative is going to be k times n u to the n minus 1, just using the chain rule. So k times n is -2 u. Subtract 1 from that, you get -2, but then times the derivative of the u. So what's the derivative of this u? -2x. And I'm taking the derivative of x. What do I have to put after this? dx dt, right? Now, this is kind of difficult the way it looks right now, so let's simplify this a little bit before we substitute in. So I have -2 times -2x, so that part's going to be 4x. This is the only part that's to the -2, not that, just this. So this could go to the denominator and be to the +2 now. And then just don't forget the dx dt. So now we're going to substitute in. We're trying to find dy dt. So we have dy dt equals. And then we're going to substitute in our x's. So we have 4 times -2 over 1 minus -2 squared squared. They tell us what dx dt is also. dx dt is 3, so I have to substitute that in. So working with the numerator, 4 times -2 is -8 times 3. On the bottom, I have to do -2 first. I have to square that first. So -2 squared is 4. 1 minus 4 is -3. -3 squared is 9. So now simplifying this, that's going to be a 1 and a 3. And so dy dt for this situation right here, the change in y with respect to time is going to be -8 thirds, and that's going to be centimeters per second. If they give us the units, then we should use those units. Okay, so that was part A, and then in part B, it's the same kind of thing. We've still got our derivative. Just going to jot that down again. While I'm writing it down, I'm going to go ahead and substitute the x's with 3's now instead of negative 2's. And then dx dt didn't change any, it's still 3. So in the numerator, 4 times 3 is 12. Here we've got 3 squared, that's 9. 1 minus 9 is negative 8. Negative 8 squared is 64. We still have that 3. So then we just want to reduce this. Both of these can be divided by 4. So divide this by 4 and divide this by 4. And so we're going to get 9/16 centimeters per second. Any questions? Alright. So what I want you to do is work on the bookwork. That's just on page 149. We're doing 1 through 6.